Alright, so we have problem number 3 in Gauss law. Consider four Gaussian surfaces. And what does it mean by these Gaussian surfaces? It means um, we have four containers. So each container, they have different amount of charges. So we have container A, B, C, and D. So if we look at this diagram here, we have container D that contains all of the charges, container A that contains only Q1, Q2, and Q3, and the rest, they also have different charges inside them. Now, remember, in Gauss law, we are only using the charges that are inside the container. Okay, and the formula for the Gauss law is flux. Let me write it out. It's the flux equal to the amount of charge inside over the permittivity. Okay, so that is the formula that we will be using. Now, the question is, how do we get the Q on top? Remember, it's the Q, the charge that is found inside the container. Okay, so let's say, for example, letter A. Letter A says, determine the total electric flux of B. So it means we'll be using the Gauss law because it's a container with charges inside, and the container B is this one, the green one. Okay, green one. We have charges inside the container, Q2, that is negative 1.0 microcoulomb, Q3, which is 5.0 microcoulombs, and Q6, that is 4.0 microcoulombs. Now, how do we get the flux, or the total electric flux of container B, or the Gaussian surface B? So the same thing, you're just gonna use the formula, but this time let's label it with B, so we know that that's for the uh, Gaussian surface B, or the container B. So total Q, or the Q enclosed inside the surface B, or the container B, we just need to add up all those charges. So that's the other step that you need to do before we solve the electric flux using the Gauss law. So we have Q2 negative 1.0 microcoulomb plus Q3 5.0 microcoulomb, that is already positive 4 microcoulomb, right? So plus Q6, which is 4.0 microcoulomb, so that's 8.0 microcoulomb positive. Okay, all you need to do is just add them up and then put them together. It's 8.0 times 10 to the negative 6. So Q2 plus Q3 plus Q6 is equivalent to 8.0 times 10 to the negative 6. And of course, you need to use the constant value of this permittivity, which is 8.85 times 10 to the negative 12. And proceed to division. The answer is 9.0 times 10 to the 5. That is already rounded up. Newton meters squared per coulomb. So it means the amount of electric flux inside B is this much, 9.0 times 10 to the 5th Newton meter squared per coulomb. Okay. Next, letter B. It's asking for the total electric flux of D. So it means it's the bigger or the biggest container, which is this one, um, the container of all the containers. Okay, so it means the container D covers all of the charges, right? So we have Q1, Q2, Q3, Q4, also Q5 and Q6. So what we're going to do is just the same thing. The electric flux of container D or Gaussian surface D, whatever total of the charges inside Gaussian surface D divided by the permittivity. That's it. You now get the electric flux inside Gaussian surface D or container D. So all we need to do is just add them up. Q1 plus Q2 plus Q3 plus Q4 plus Q5 and plus Q6. Because all of these charges are found inside D. Okay? And the total, if we add them up, we have already the values here given. So add them up and it's 15.5 times 10 to the negative 6, and that's actually in your calculator you will get 1.55 times 10 to the negative 5. Okay, but that's fine, it will still give you the same answer. I just put it in this format, although it's not proper scientific notation, but I just put this as this just for us to see that adding them up will result to 15.5 microcoulomb. Okay, so that's how I did it, because we can actually just add them up and copy the symbol micro and then the column before we do that in the solution. Okay, anyway, so the result is 15.5 times 10 to the negative 6 for our total charges, or the total charge, I mean, divided by the permittivity, which is 8.85 times 10 to the negative 12. The result is 1.8 times 10 to the 6 Newton meter squared per coulomb. So that's the total electric flux inside the D. Now the question is, which of the two Gaussian surface B or Gaussian surface D has the bigger amount of electric flux? Okay, look at the exponent of their answers. The D has 1.8, although it's a smaller number, but the exponent is times 10 to the 6. It means this amount here is much bigger compared to the amount of B. And obviously, because Gaussian surface D covers more electric charges inside its container. Well, Gaussian surface B, or the container B, is just covering Q2, Q3, and Q6. Okay, so that's it.